Good afternoon, everybody. My name is Tassos, and I'm with RF Elements. And today we'll be doing our presentation on Noise Rejection 101. So this will be a webinar talking about the benefits of our horn antenna technology and how it differs from the older traditional patch array sectors that lots of people are still using today. So at RF Elements, we deliver fast, sustainable wireless, and we do this by a couple of different ways. The main way is by offering antenna solutions that have very high noise rejection. Our symmetrical horn antennas have a very good ability to reject noise by creating antenna patterns or RF patterns that have zero side lobes. And these zero side lobes are very important in antennas today because they help reject noise by making sure your radio only sees zero loss output apparatus. So this zero loss and this noise rejection coupled together gives you the massive scalability that wireless ISPs need today. The WISP market is growing by leaps and bounds every day. The necessity for internet connections in everybody's home is growing faster than it ever has, and also the demand for faster and faster speeds for each of these connections are growing. So in order to be successful as a WISP today, you need to have a network that gives you the ability to scale on a massive level to deliver these wireless products to your customers, and RF Elements delivers antenna solutions that will allow you to do that. So if we look at kind of the key challenge, some of the major challenge in wireless today is basically spectrum, right? We have a very finite amount of spectrum that we are allowed to use, depending on where you are in the world. That legal spectrum in which you can operate in changes. Some places have more, some have less, but regardless of that, the challenge is the amount of usable spectrum that you actually have within that limited bandwidth that you can deliver. So RF Elements symmetrical horn antennas help deliver to address the challenge of spectrum. So the problem in achieving or maximizing the spectrum that we do have is basically the antenna radiation patterns that exist with today's legacy antenna systems. So antenna side lobes are inherent to most legacy antenna solutions that are deployed today. The very typical patch array antenna, no matter how they're created, it's inherent to that RF design that side lobes actually exist. And these side lobes create huge problems for you as you try and grow your network and as you try and increase the performance of your network. So these legacy antenna technologies really don't allow for an exact beam angle and don't have the appropriate radiation properties, right? So these antenna technologies have very inconsistent beam patterns, very inconsistent gain across the different polarities. And again, this kind of legacy approach to antenna technologies really creates the problem that we're seeing and helps us, and stops us from achieving, what we need to do as a wireless ISP. And this RF noise is basically a result of this old technology being deployed in the field. It's really causing huge issues for yourself when it comes to co-location, but also with other WISPs, right? So, today the density of wireless deployments are growing, not only for your WISP, but right, you're finding yourself co-located with other WISPs, not only sometimes on the same tower, but at least in the same town or in the same cities, right? So it makes competing and working, and doing frequency planning with these competing WISPs, whether they're partners or not, makes it very difficult to do because of the legacy antenna systems that are being deployed. And basically, the RF noise is purely from deploying this outdated gear in unsustainable ways. It's really not sustainable and not possible with old technology. And our horn antennas will give you the ability to, work around these issues and help you deploy much better wireless networks. So again, patch array antennas, right, really have inconsistent beam angles, and they have huge side lobes. And these side lobes protrude not just from the side, as these as the tense of the word side lobes means. They also come out from the top and the bottom, and really out the back of the antenna. And this is one of the biggest problems that we see with patch array antennas. So let's look at some other different types of antennas. Let's look at like an omnidirectional antenna. For all intents and purposes, an omni antenna is really just one big side lobe. Because it radiates in 360 degrees, it's consistently transmitting signal to where your customers are not, just not where they are. So these areas of coverage where an omni is able to send and receive signal from can be practically, categorized as a side lobe, right? It's an area of transmission or an area of reception that your radio doesn't really care about, but it's forced to have to listen and deal with these issues. So an omnidirectional antenna really doesn't have much of a place in today's, really high speed 802.11 AC, 256 QAM networks today. Makes it really difficult to, again, grow your network and expand and really deliver the types of throughput that you need, because there's just way too many competing stations out there that will affect your omnidirectional antenna, and therefore, again, it's not really the best antenna to use. If we look at a patch array or your legacy traditional sector, this is what the pattern looks like in 3D, and we can see the highlighted areas, which are the side lobes. You can see that they protrude off the top and the bottom of the beam, but mainly off the back. And if we look at it from the two-dimensional view, you can see the area of coverage of most traditional sectors is, again, much wider than your actual coverage area. So not only are the side lobes in red in the back sending noise or sending signal in the opposite direction or in a direction that's not intended to be sent to, it's also receiving signal from those directions. If we look at the oversized main beam pattern for where your customers are supposed to be, you can see that they usually have really high gain beyond the coverage area, and therefore it's a useless area of service and becomes a receptor of noise as well. So all this really affects your overall network throughput of that access point, and becomes a huge problem for you to deal with. The same goes for parabolic dish antennas. So if we look at the highlighted areas, again, this is the side lobes, the secondary lobes that come out of a parabolic dish antenna that are, again, other noise receptors or noise transmitters outside of the main beam, the part in which you really care about. So if we look at the areas of these side lobes, we can see how when you have competitor stations out there, competitors' backhauls, or even your own backhauls, you're really opening yourself up to having a radio that's able to hear and able to talk outside of the intended path in which you're trying to create, and therefore makes a huge problem for you in trying to build out your networks, keep your network latency down, keep your modulation rates stable, and really it's just an all-round worst case scenario for an antenna design. So again, side lobes are a huge no-no. Here we're looking at just a single AP and a tower. Right? So we see these huge areas of noise reception, but as we start adding our second sector, or even our third or fourth sector later down the line, we can see where all these side lobes start to interact and overlap. And they're not only interacting and overlapping with just the co-located APs, but the intensity of these signals are so strong that they even are capable of reaching your CPEs out in the field as well. So this makes it very difficult to be able to RF plan, for instance, right? So, frequency reuse is a huge thing today because, again, we have very limited spectrum. And even though you may be using a different frequency, a radio on a on a upper band still can hear at really high intensities another carrier frequency, and the radio has a really hard time filtering this out at times, and therefore creates a lot of work for it, right? So these side lobes really, again, drag down your network performance and really create issues, not only for your co-located APs, but also for potentially your other towers. As networks are designed today, the coverage areas are getting smaller and smaller, which is great because really these shorter distances are really required for these higher modulation rates that a lot of radio manufacturers are putting out today. And the problem is as we shrink these coverage areas, we're not shrinking the gain and we're not changing the antenna technology. So we're still using, really high gain patch array sectors to cover even smaller areas. And that makes that side lobe signal even stronger. So if you have pops every couple of miles, you can just imagine how intense the signal is from one pop to another when you first can't control the radiation angle of your antenna because it's super wide, but also you have side lobes that are sending signal in opposite directions. So where you think you might be able to reuse a channel because the channel you want to use is transmitting north, you really have a really intense side lobe transmitting that same channel in the southward direction and therefore causing all sorts of issues for you. If we look at it from the point-to-point standpoint as well, so when you co-locate a second backhaul onto your network, again, these side lobes are really large, and now they start interfering with your other point-to-point links. Never mind, you also have on top of that your point-to-multipoints usually on that tower. These side lobes are so intense because as you increase the gain of an antenna, those side lobes increase in intensity as well. So now you start having to compete with your competitors' APs that might be on a different tower if not co-located with you as well. These side lobes are so large that, again, you can start creating issues and start interfering or receiving interference from competitor stations as well. So the higher the gain of the antenna, the larger the intensity of the side lobes are. So all around, it just increases the issue that you're having and therefore reduces the overall network throughput capabilities and makes it very difficult to achieve the spec speeds of the faster radios that manufacturers are putting out today. So the solution is using antennas with precise beam angles in those side lobes. If we had antennas that had very precise beam angles, so you knew that outside of the specified beam width, the signal drops off really fast, you wouldn't get all this bleed out into other areas, and you can send your signal or create a coverage area that covers the actual area you want to cover and nothing else. Without side lobes, we wouldn't have the issue of co-location, and we really wouldn't have the issue of again, interfering in, let's say, the mini pop or micro pop world with other, really closely located pop locations. So horn antennas give you that. If we look at the same point-to-multipoint links and we start replacing them with, let's say, our ultra horn, which has no side lobes, you can see already that the improvement is there, right? Your first two co-located links on your tower now have practically zero side lobe interaction. You're still potentially picking up signal from competitors' backhauls who are still using the old parabolic legacy type technology, but you've at least increased your performance. You've at least, increased your noise resistance on your actual backhauls, therefore improving the performance of your backhaul radios. And now we can see if your competitors actually use the same technology as you, how all of a sudden frequency planning becomes much easier. So it's possible to now coordinate with competing WISPs. It makes it spectrally more efficient for yourself, so you know what frequencies you're using on what azimuth, and therefore where you can reuse those frequencies in other backhauls or on other towers, or again, if you're using GPS synchronization. All this stuff comes together, giving you the ability again to use channels more efficiently without side lobes. You also can use smaller guard channels, again, because the bleed off isn't there, like you have with traditional patch array sectors and parabolic dish antennas. So here we're going to look at side lobes in linear scale of a parabolic dish. So this is like a 10-mile link. So we can see what the side lobes look like, and as far as the effective distance of them. If we look at the horn antenna on the right, you can see there are no side lobes. So those secondary lobes that come out the back, again, it depends on the gain of the antenna. And even though those side lobes are usually measured at like the -15 or maybe even -16, the intensity is so strong that you can go up to 2 kilometers on those side lobes and still affect other networks and also affect your own network. So this is just to put it into scale to see that when you're looking at your polar plots or your RF plots that come on spec sheets, those side lobes look really small. But if we look at the linear scale relationship to a 10-mile link, right, to your standard kind of average side lobe, you can see that those side lobes go over a mile. If this link was a lot smaller, again, this would make a much larger difference. And a horn antenna, a directional horn antenna, is definitely much cleaner and much more efficient. So if we look at point to multi-point, the same thing applies. Let's say we just removed one of the sectors that you had and we replace it with 2 horn antennas, right? So let's say 120 degree, we just replace it with 2 60-degree antennas. So your network throughput for those APs already starts to go up because you've now reduced at least one source of side lobes, one source of interference, one source of, again, unintended signals, because the horn antennas themselves are now not interfering with each other, at least at this level. Okay, but they're still having to deal with the other traditional patch array sectors that you have on your tower. So, just a couple of horns by themselves increase performance, but you never really see the overall performance increase that you would on a network until you go to nothing but horns. It's when you have nothing but horn antennas that you truly start to see the immense benefit of horn antennas once you take away the huge variable of those patch array sectors that you still may have on your network. So horn antennas by themselves are the ultimate network throughput increaser, right? It's the best way to eliminate the noise and be able to scale your network up from that point. If we look on a linear scale again of the side lobes for a patch array sector, you can see here like a standard, kind of average 5-mile coverage, and we can see the side lobes to scale in pink. These side lobes again are really, really large. They can go out as far as like 1.6 kilometers at a really high intensity. They go further than that, but again, as you go further, that signal starts to bleed off. So you can imagine with having an intensity of, a signal that's intense enough to be received at 1.6 kilometers or a little over a mile, you can see that it's certainly going to cause havoc for your co-located sectors on your tower. Never mind, again, if you're using this in the pop or micro pop world, right? These new style APs where people are doing kind of pops every mile or 2 miles, you can see how this could really start causing havoc on your other ones, even with GPS synchronization. Makes it very difficult because, again, these side lobes are usually coming out the back of the antenna, and it's not part of your GPS sync planning or channel reuse at this point. So it's a huge problem. So really, there's more to noise rejection than just rejecting noise. It's really about gain. Here, if we look at the pink, we're seeing the area reception of a traditional sector. The area of blue is the area of transmission based on your EIRP or what your gain is and your output is. So we could always adjust the output power of our radio and reduce the area of transmission, but we can't do that for the area of reception, right? So you can see if you use a lower gain, appropriately spec gain horn antenna, as you use that lower gain, you're now reducing the amount of noise that the radio can receive, and therefore makes your user experience much better. So if we watch it here one more time again, we can see that the receive signal is pretty intense for those 3 pins because they're within the gain sensitivity of that sector antenna. If we were to reduce the gain of that sector, all of a sudden now those signals are minimal or marginal, right? So using the proper gain antenna for the area you want to coverage is really, really important, right? So if you're only covering a couple miles, you really have to reconsider using the highest gain sector you can find, those 19, 20, 21 dB or even higher patch array sectors that are being used today. Horn antennas come in 7 different sizes, everything from 30-degree to 90-degree and 10-degree steps. And with these widening of radiation patterns, you also get lower and lower gain. So a wider, smaller gain symmetrical horn antenna might be much better suited for a close-in type coverage than these really high gain traditional sectors. So there's really like 3 rules for noise rejection, right? So, deploy antennas with no side lobes, right? So when you're making your antenna selection for your WISP, you really have to pay attention to the spec sheets. You really want to find antennas that have no side lobes, right? Or at least the smallest side lobes as possible. So using RF element horn antennas is clearly the answer there because we have 0 side lobes. So you can deploy our antennas and have the first rule of noise rejection. The second rule is, install antennas with the appropriate beam angle and only propagate and receive signal where it's needed, right? So again, if we look at how traditional patch array sectors work, their beam angles are very inconsistent. Typically your vertical is different than your horizontal beam in these MIMO systems, right? So you might have a wider beam in vertical, a more narrow beam in horizontal, and therefore you're not really getting a very accurate coverage area. So it varies a lot between the polarities of these antennas. Using RF elements horn antennas, you get extremely precise beam angles. A 30-degree horn transmits pretty much 30 degrees, and then the signal really starts dropping off extremely fast as you go beyond that 30-degree coverage area. So using RF elements horn antennas give you the ability to, again, have very precise radiation angles and very high control of the beam angles and the propagation of these signals. And then lastly is, again, use antennas with moderate gain, right? You don't have to kill everything with high TX power, right? So keep things within your EIRP limits. And also, if you're not trying to cover, long distances, turn your power down, right? This is really going to help increase, the performance of your particular tower site, but it's also going to help you later as you build out your network, as you put up your second site. If you're not blasting all this noise everywhere, there's a very high probability that your next tower site is going to be able to function better because you're not putting out as much noise because you're controlling your TX power, right? And horn antennas again give you a large variety of gain and beam angles to be able to build that out and deploy your networks much smarter and way more efficient than patch array sectors allow you to do. So I'd like to also let you guys know about some upcoming webinars we have. We have a new Antenna Mythbusters webinar that we're working on that I'd like you all to keep an eye out for. This is going to be a great webinar to really go into much more detail about antenna specs and kind of some of the myths behind some of the things that you see and some of the magic that some manufacturers put into their spec sheets and kind of misguide you by really focusing only on, let's say, high gain, or only focusing on the front to back ratio, depending on what you're looking for. So this is a great webinar that we're working on that's coming out soon. So keep an eye out for that. We'd ask you to join our community. We have a pretty active forum, rfelab.com. Great place to go find information. Very high probability if you're having a problem, there's probably a post on our forum for another WISP that's having a very similar problem to you, and it's a great resource to kind of figure out what you can possibly do with our technology to help alleviate these issues. And then we have a lot of customer feedback. Join our YouTube channel if you haven't. We have a huge listing of customer testimonials, customers who are using our antenna technology and explaining how it benefited them. And the best part about these customer testimonials is it's not us, right? I know most users don't want to hear the manufacturer telling them that their product is great and they should buy it and try it, right? There's nothing better than you actually hearing from WISPs like yourselves that are doing exactly what you do day in, day out and dealing with the same issues that you're dealing with. So if you go to our YouTube channel, you'll see a lot of videos there that explain how WISP successfully deployed our technology and hopefully how it can benefit you. So stay tuned. We're working on a lot of stuff. This is just the beginning for us. Our symmetrical horn antennas were kind of the first entry into the market for our game-changing technology. We've doubled down on that now with our ultra horn technology, which some of you may know about for point-to-points. Again, it's the same, no side lobes, really clean noise rejection for point-to-point links. So follow us. Join our forum, rfelab.com. Visit our website, rfelements.com, or check us out on social media. We're all over the place: YouTube, Facebook, G+, LinkedIn, Twitter, you name it, we're there. I'd personally love to hear from each and every one of you. You can always reach out via email or find me on social media, and we can communicate that way. I'd be happy to help you in any way, design your networks, whatever questions you may have, I'm happy to answer them. And at this point, I'm pretty much done with the presentation. So I'd love to go to some questions. If you haven't yet typed in your question, please add it to the chat now, and I'll answer it as detailed as possible. Thanks.
Thanks, Tassos. There are some questions that are coming in. We do have one that's asking, are there horn antennas for LTE radios?
So no, not at the moment. LTE is basically in like the 2.5 or 3.6 gig range, depending on which part of the LTE spectrum you're in. It's definitely something we're looking into, right? It's something that's on our roadmap to address and potentially create something from. But at the moment, no. Our horn antenna technology is currently in the 5 gig only, right? So all our 5 gig antennas cover the whole 5 gig spectrum, but there's no 2.4, no 2.5, or no 3.65 at the moment.
Okay, thank you. We have another question, and they're asking, do you have an update or an ETA for the 21 dBi ultra horns?
The update that I have is it's still in progress, right? I don't have an ETA to share, unfortunately. It's on the immediate roadmap. We have a couple other products like the AirFiber twist port adapter, AirFiber 5X and HD twist port adapter that people have been working on. So it's really close in the timeline. Hopefully in the next few months we'll see it. Again, I don't have a definite date to share, but it's getting really close. It's definitely in the front of the list, not the back of the list for sure.
Awesome, thanks. I don't see any more questions rolling in. Can give it a few more minutes.
Yeah, if anybody has a follow-up question, please. Like I said, we have plenty of time, so don't be shy.
you have anything additional you want to add on to those?
No, just again, just the best thing I can say is just, plug into the social media groups that we're part of, Facebook, LinkedIn, and Twitter. Again, a lot of exciting news, a lot of information is being shared online for other WISPs. Issues are being answered. I mean, really, that's the big thing, right? People want to know before they start a new technology whether or not they can trust it, right? So I think the first step is, do some research, and test it out for yourself. Our horn antenna technology is fairly cost effective. It's really not that expensive. So try one out. If you have any questions or you have any problems, reach out to us right away, and we'll help sort it out.
Thank you. We do have one more that came in. They're asking, do you have any plans for other antennas in other frequency ranges other than a 5 gigahertz range?
Yeah, so I like the LTE question, right? So the answer is yes, right? As far as what frequency range, pretty much, I think 3 gigahertz is probably the bottom of the range for us. So something in the, the 3 to 3.7 or something like that is what's coming next as far as plans for us at the moment.
Okay, perfect. I think you probably just answered this question. They're asking if there's a plan to deploy a 3.65 gigahertz scare. So.
Yeah, again, most certainly. I mean, we're seeing it. It's definitely not something that we're unaware of. We see the growth in that, but RF elements as a whole, we really take our time, right? Unfortunately, I know that annoys a lot of people, but we have the reputation of creating a product that does exactly what we say, right? And when you rush a product to market, you make mistakes, and sometimes you make sacrifices. And these sacrifices in performance is something that we're absolutely against, right? So, just because it's not out now doesn't mean we're not working on it, right? A great performing product takes time, and definitely 3 gigahertz is something that we're very aware of, and hopefully you'll see something.
Perfect. There's another question asking, in some of the photos, they see RF element horn antennas on top of one another. Mm-hmm. Do you need to have separation, especially shooting the same direction?
Yeah, great question. Great question. So, a horn antenna is still an antenna, right? It's incredibly unique and different than others. And its unique noise rejection qualities allows you to do things with our antennas that you can't do with others, right? So you still need spatial separation, right? And just like any other antenna, the more space you give it, the better. The difference is that you can get away with a lot less space with a horn antenna because, again, it's so precise, there's no side lobes, and there's such great noise immunity that you can, again, stack them a lot closer than you could ever do with a patch array traditional sector. And in most cases, you can do this successfully without GPS synchronization. So that's kind of the broad view answer, right? So now to specifically answer the question, yes, you can mount them, and many people do, as close as you see them. I mean, typically, the horns are at least like 1 foot away from each other. That's what I would say is pretty much the absolute minimum that you want to do, is at least 1 foot. Again, if you have more than 1 foot, use it. What I say is, if you have a 10-foot vertical span or area, or even 5 foot, don't start stacking them right on top of each other. If you're putting up 2, put 1 at the top, 1 at the bottom. Give yourself as much room as possible. So that way, when you put your third antenna up, put it in the middle, right? And then you start, cutting that space in half. So don't stack them together from the get-go, unless you absolutely have to.
Perfect. And there's just a compliment on the 3.65 gigahertz. They agree that would be a great idea.
On what? Sorry?
The 3.65 gigahertz, the question previous.
Yeah, we know. Definitely, as I said, it's definitely something on the front of the map right now.
I'm not seeing any other questions rolling in, so do you want to wrap it up then, or wait a little bit longer?
Yeah,
We
again,
haven't answered, so.
just wait a couple minutes. If we don't see anything, then we can sign off. People are still logged in. So if you have questions, ask them now. That'd be great.
Don't be hesitant. Tapas is great in answering questions.
Don't be shy. We don't say who asked the question, so. All right, I guess if there's nothing else then.
There's nothing else. If there are any questions later on, you can go ahead and Tapas gave his information. You can always reach out to us at Streetwave, and we'll always be able to help you answer all those questions.
Thank you.
Thank you, guys. Have a good day.